I think we are with the time a little short, but I can't say, I can't sacrifice too much. So first of all, this is a picture from 90 here in the lab. And today I realized that, Massimo knows that we used to say in Italian that we always have the capo di tutti i capi, which is the chief of all the chiefs. And I think now we have you as the capo of tutti i capi. So you have a big responsibility because the whole atomic community is somehow hold on you. And I cannot resist to show David Weiland and Bill Phillips really working in the lab and tightening bolts. So anyway, your presence in São Carlos has been very remarkable, all attracted by Dan, and we are very thankful for that. I'm going to show to you just a few slides about quantum turbulence. This is a topic that we started here in 2009, and we are carrying on some research on this. As you know, I have to skip a few slides, but I have a big group: Sergio, Gustavo, Rodrigo, Monica, Caio, Kilvia, Pedro, Guilherme. Wow, it's a big list. And they are working now in a few experiments concerning turbulence. And quantum turbulence is always interesting. I remember when I was a student and Dan was speaking a lot about quantum chaos, and we didn't know what that means, but anyway, confusion in the quantum world is always very interesting. And of course, if you look, science is taking turbulence as a challenge for a long time, and they are stuck. They cannot understand many of the features, but everybody is interested in classical turbulence. We want to understand why shake the airplane and what are the limitations in industry that turbulence introduce. But we are interested in the quantum world, but there is a connection. If we understand well one thing, we may have hints about the other one. So, as Chris said, in the quantum, this is a system where in the quantum world, things are more simple. The vortices are quantized, they are equal each other, and in the classical world, no, that doesn't happen. So, of course, we know this diagram already. BEC is being a model for many things, and of course, it is a superfluid. People generate vortices on it, so why not turbulence, right? So it seems to be a natural thing to do. And turbulence in the quantum fluid is something introduced by Feynman, I think, in 1955. And the vision is that the image is that have those vortex filaments all tangle in space and reacting and reconnecting and having cascades, as Chris already showed to us. So, to be very simple, the idea is, Eric is here, he knows how to generate the vortices, just steer the condensate. And Tsubota said, okay, let's steer the condensate this way and then steer that way. We're going to generate vortex line everywhere, and then they're going to start to cross each other and generate turbulence. So, well, based on that idea, we start and we demonstrate in a little different way, but a kind of a variant from this idea, how we generate vortices, how they cluster in vortices and anti-vortices, and then the emergence of turbulence in the cloud, and the self-similar expansion that Professor Fetter already explained a little bit in his talk, and effects of the finite size, and many others, and the red one are the ones that we are working now, and we think we have the total energy spectrum, which is a kind of the desire object for the theoreticians, is how is the spectrum of energy in this system. And we think we have some evidence of what's going on. So to be very simple, what we do, we shake the condensate. I call that a washing machine for the condensate. We started to steer a little bit in all directions by shaking it. And as a result of this, we wait a little bit, and we have vortices that are formed. So if we shake very gentle, we just see a very well-known mode, which is called scissor modes, which is inherent of the superfluid property. But then if you go a little further, we start to generate vortices, and then we generate more vortices, and then we generate configurations of vortices. This is a paper we published showing that there is evidence that we had vortices and anti-vortices, and then they cluster together in different configurations, either in a line or in a triangle. And of course, if you want turbulence, you want to proliferate the number of vortices. You want to multiply, you want to have a lot of vortices. So we start to pump energy in this system by shaking, and the number of vortices start to explode. And when that happens, the cloud changed a little bit the behavior and became turbulent. So we start to have a vortice going in all directions, crossing and perpendicular everywhere, and that is what we characterize as an emergence of turbulence. Together with this configuration of vortices everywhere, it comes some nice different behavior, like the self-similar expansion and a few others. So I'm going to jump this. This is a nice evidence and theory showing that this somehow is an evidence that you have a vortex everywhere distributed. The self-similar expansion, which is something that's neither a pure superfluid nor a thermal fluid. So it is expanded in the way that's born, and this is an evidence that we investigate, and I think Professor Vetter already explained to you the theory. Now, there is something very interesting. It's related to the fact that our cloud is a superfluid, but it's a confined superfluid of finite size, and we can more or less resume, collect everything we observe in this diagram. When we excite this by shaking in different times with different amplitudes, we see domains of behavior. So we see either these scissor modes, these bending modes, or we see vortices being proliferating, or we see what we characterize as a turbulence with vortices configure a tangle of vortices really distribute all around the space. And then if you try to put more energy, this system must break in little domains that we call granulation, that we are still investigating what it is. And we even have some collaboration with Randy Hewlett in a 1D where we do similar things. And the things happens there too. As you saw in the diagram, there is a kind of region separating the behavior of this cloud concerning turbulence. And this is a consequence of the finitude size. The fact that the system is finite in size, and the number means that we cannot introduce there as many vortices as we want. We start to pump vortices into this cloud, and then suddenly we are occupying the whole cloud with vortices. And if we try to put more vortices, shaking more, well, these start to react faster than generating more vortices, and then that's why we see this line. This is being calculated. I'm going to jump all this calculation, but basically we understand that must be a kind of frontier of this behavior when the system is finite. Well, Tsubota from Japan, which is one of the biggest authority in turbulence, I think, in superfluid, he simulate, and he could get exactly by introducing the excitations the way we do, he could see formation of vortices proliferation and evolution for turbulence. And of course, to be able to reach this, he had to introduce in the mean field approximation dissipation, artificially introduced. And we saw in the lab that was easier to produce this whole thing when we had a large thermal cloud than when we had a small thermal cloud. We never investigate this effect in the depth that we would like, and that's what we are preparing to do now, is the influence of this thermal cloud on the formation of on the evolution to turbulence. But it seems to be important to have dissipation. Well, then we did a few experiments to show that when we shake in the way we are shaking, a kind of second sound excitation takes place where the thermal cloud oscillates out of phase with the condensate, and that's important in the generation of vortices And we even could see the moment where the first vortex seems to start to appear when we excite. But of course, as I told you, if we speak to a theoretician, they want the spectrum. They want the population in the momentum space. Where is the energy of these in scales? And Chris already introduced this. Is important, maybe is the most important result that is in turbulence is the Kolmogorov type relation, right? So I'm not going to speak about this a lot, but this is for you to see how we see the absorption of the cloud when it's a regular condensate and when turbulence takes place. And well, I'm going to jump to all of this, but in your system, it's interesting because if I let the cloud to expand freely, it's going to tell us a little bit about the energy. In fact, it's going to tell us a lot about the momentum that was contained in the sample. And that's what we're doing now. We are trying to measure the momentum by let expand. We made some models, and I think by the first time, we are able to kind of come with the energy distribution of a turbulent cloud. This is the energy distribution of a non-turbulent cloud, but when the cloud became turbulent, I cut part of it. Well, when it became turbulent, very interesting features start to appear in this energy spectrum, or momentum spectrum here, if you will. And the first evidence is that a scaling law, which means there is a part of the momentum range where the energy scales as a power law, which is something very characteristic of the classical turbulence, appears in the system, and that's what we are examining now. And of course, there are many models that people are calculating. The way we do is a 3D. You know, it's a little different to the proposal of Chris or Brian Anderson, where they want to do in 2D. And then, of course, people are having a hard time to simulate a 3D superfluid confined in the harmonic potential to generate everything we observe. But things are very promising, and we are very excited because we published like 10 papers, and we are getting a lot of citations. We even made it to the point editor choices and point of view. And I think quantum turbulence in those confined systems may be another very interesting applications for Bose-Einstein condensate and superfluid, because we already have evidence that we can see some of the elementary effects taking place, like reconnection and things like this, and I think this will be great. This is a diagram that I stole from Tsubota, where he was showing superfluid helium. They see arrays of vortices, and then he said in atomic BEC, people also see the lattice of vortices. Well, in helium, we do see turbulence, but he said that in BEC was still empty, and I think we are just starting to fill it up, that box, and this will be, I think, a promising land for new applications of BEC concerning the superfluid property. Well, I rush a lot because I want to finish 4 o'clock so we can continue our program. Then, thank you very much. You know, you are a model for us. We follow you. So I think that's why you're so careful. You knew from the very beginning that this will happen. So what Rick said is true. I mean, you're very careful because you knew somehow, you have to tell us, that everybody going to follow you. You are our model. So maybe that's why you are so careful about everything. And of course, I mean, following you, we cannot do bad science. Thank you very much.